Okay, so let's take a look at homework 2. Hopefully you get a chance to review the solution already, and also review my comments for the solution that you provided. So for homework 2, for first question, hold on, let me zoom in. So the first question is really trying to just try to brainstorm if when you try to build a model, you want to think about different aspects. For this particular example that we discussed here says a company with a fleet of trucks facing increasing maintenance costs as the age and mileage of trucks increase. And then asking you if you can identify a problem with studying and list the variables that affect the behavior you have identified, and which one would have it's probably can be neglected, or which might be considered as constants initially, and how can you go through this process. So for example here, as a solution here, you can see that, hold on.
Hey, we can't, we're not seeing your screen. Yeah.
Okay, so now you can see it. Good. Okay, so and then so the problem is, let's say that the solution says, okay, here just one of the solutions that you might think about. So for example, the independent variable could be vehicle age, vehicle mileage, and then dependent variable apparently would be the maintenance cost. And then what else could affect the maintenance cost? It can be vehicle weight, right? It can be elevation rise. It could be the indication, meaning that how much, what's the percentage of the mileage that actually involves elevation change. That's only a possibility. You can also think about maybe the how much percentage of the mileage is actually highway mileages, things like on that front, right? And also average speed driven and average time of mileage between oil change, average gas mileage. All of this could be a consideration. So this is just give you a sense on what you might be considering. So that's for question 1. So for question 2, we're trying to see if there's a relationship between y and x powered by 3, x cubed. So one thing is you can just do the transformation first. X cubed is x powered by 3, and then you try to get a new variable which is called, let me zoom in a little bit more. And then you call it x cubed, and x cubed is really x powered by 3, and then you build a linear model and see whether it actually makes sense. And then apparently that here y versus x cubed has a strong linear relationship there. And then we can see from the above plot y positively correlated to x cubed is a reasonable assumption. The best fit line slightly offset. Of course, you know that at this stage in this chapter, we haven't studied linear regression yet. We didn't discuss how to take a look at the residual, how to see whether this is the best fit, things like in that nature. But apparently in this chapter, homework 2, chapter 2 is sufficient here that you, if you can identify this relationship. Okay, so for next question, page 94, number 4. And then a question is saying that, okay, lumber cutters wish to use readily available measurements to estimate the number of board feet of lumber in a tree. Assume that they measure the diameter of the tree in inches at waist height. Develop a model that predicts the board feet as a function of the diameter in inches. And then the following is the data. X is the diameter of the pie in inches, and y is the number of ball fit divided by 10. And then question part A, consider two separate assumptions allow each to lead to a model, completely analyze each model. For first one, assume that all the trees are right circular cylinders and approximately the same height. And then problem identification predicts the number of ball feet of lumber in a tree from the diameter at waist height of a tree. And from this model, we will assume that ball feet has a relationship with the volume of the tree. So to calculate VT, we will assume that all the trees are the same height, and we will approximate that height as the average height of a pine, HAVG, and then the volume of tree would be VT equals to H average times A, where A is the diameter, which is the cross-sectional area of the measured tree, which can be calculated by the diameter. And we know A has a positive relationship with D squared, which is the diameter squared, and then so that you know that VT has a relationship with H average times D squared. And finally, BF ball fit is a relationship of D squared. We drop H average because it is a constant in this particular case. So let's take a look at the data, and then X is given, Y is given, and then get X squared to see whether there is a relationship, linear relationship between Y and X squared. And good news is it has this relationship, and we can identify the coefficient. So it looks like it's a reasonable approximation. Even though not perfect here, it is somewhat perfect in my opinion, even though we had this comment here. And then if you look at the second assumption, assume that all the trees are right circular cylinders and that the height of the tree is proportional to the diameter. So this is another possibility. And then we say, okay, H is proportional to D, so that V is D times D squared, so that V is has a linear relationship with D cubed. So we do the same thing, and then we find this relationship. And then it is reasonable approximation, and then the next question is which model would be better. And then to compare the models, let's plot the actual data versus the predicted values for each model. And then we see that apparently that the red line represents the second model, so that we can see that the red line is clearly a benefit of the actual data, so that second model is better representation. So can you see that now? No? You cannot see the graph. Maybe because of my new Windows 10, this PDF version has some sort of issues. But you should be able to see it though. Oh, you can see it now? Okay, good. So that's the idea. Just apparently we have other better ways to look at the relationship as looking at the residual plots as we discussed later on in the chapter. So that way we know which one is better. Shazia, so can you see the graph now or not yet? Okay. Okay, good. So if we continue And then for next question, discuss several factors that will completely ignore your analysis of the gasoline mileage problem. Some of this that you can think of. General discussion. Basically, I think everyone got it. And then this question is regarding tests exist to measure the percentage of body fat. Assume that each such tests are accurate at many carefully collected data are available. You may specify any other statistics such as waist size and height that you would like to collect. Explain how the data can be arranged to check the assumptions underlying the submodels in this section. For example, suppose the data for males between age 17 and 21 with constant body fat and height are examined. Explain how the assumption of constant density of the inner core could be checked. And then how do we check the assumption underlying submodels in this section? So how do we test the assumption of constant density of the inner core? If we have good data on percentage of body fat, then we have a good measure on the height of the inner core, the weight of the inner core. According to our model, we have W in equals to K2 H cubed. By collecting the height, weight, and percentage of body fat, we can calculate K2. W in would become W in equals to W total 1 minus P BF. We can now calculate K2 by analyzing the relationship between W in and H cubed. We can also use the body fat percentage to test the model. Suppose that W out equal to K sub 3 H squared plus K sub 4 H cubed. Again, this is done by recognizing the W sub out equals W total times P body fat, percentage of body fat. We now have enough information to calculate the coefficients K3 and K4. This is a follow-up of some of the tests. I mean, some of the examples in the classroom in the textbook. So that's everything for homework 2. In general, I think homework 2 is actually pretty straightforward, right? And then, do you have any questions so far? Okay, and also if you have any questions regarding the grading on your homework, if you are not sure, and then we can discuss that as well. If you prefer individually, send me an email, or if you want to discuss here, there's no problem at all. So let's continue with homework 3. Hold on. So homework 3 is much more lengthy, and then even though you only need to choose 3, but here I think it's more than 3. It's around oops, yeah, it's around 4 or 5 questions. Okay. So for the first one, 6 or 7. Okay, good. Thank you. So for the first one, the table gives a elongation E in inches per inch for a given stress S on a steel wire measured in pounds per square inch. Test the model E equal to C1 times S. And then by plotting the data, estimating C1 graphically. And then see from the code, you can see that, so essentially you have the S and E and trying to plot that relationship and then estimate that graphically by using 2 observations, difference between the last minus the first divided by X difference, S difference. x, meaning I'm referring to the independent variable. And then here Sn minus S1, and then you can get C1. And then final intercept at -20, because it's graphically, so apparently it's relatively speaking, it's approximation. It's really not by no means going to be accurate. And then using the model EC1S, it is reasonable to use the last data point to estimate slope. Doing so, we get C1 equal to 3.9. As I mentioned, actually, in some discussion from some students, from some discussions and questions from the students, you really not necessarily need to pick the data points that that was picked by the solution. You could pick some other points as well, and then the solution could be slightly different. And then if we don't have any intercept, then we can see that you can estimate the coefficient being 3.9, which is shown in red. If you look at both of them, apparently the blue line fits a little bit better than the red line. And looking at the second question, we were asking, okay, this one is probably take a little bit longer to explain in general, but at least we have a solution here so we can go through. So number one is we have this x and then we have this y. And then many students actually started with trying to estimate the linear relationship using least squares, just trying to build a linear model. Then apparently it's not correct because the objective function here is trying to minimize the largest deviation between the data and the line. It's not saying to minimize the least squares of the estimated value and the actual value. So that's the difference. But in the example in the textbook, this question is pretty much the same as the example that we went through in class on the Chebyshev inequality. So if we take a look at the solution here, let's assume that yn minus fxn equal to rn meaning the deviation for all the 6 points, and then fxn is axn plus b. So far so good, and then we find rn equal to yn minus axn plus b, so that we have this relationship can be simplified as yn minus axn minus b. And then we're trying to minimize the largest deviation. Assume that the deviation is less than or equal to r, and then we use similar trick so that we can use Rn larger than or equal to negative r and less than or equal to r, so that we have those two relationships. One of them is r minus In larger than or equal to 0. The other one is r plus In larger than or equal to 0. Meanwhile, we have to have this relationship that r minus yn minus 8xn minus b larger than or equal to 0, which is a transformation of the previous two inequalities. And the next one is r plus this, also I minus those, and r plus that. So in that case, if we want to minimize r so that we have all these constraints, these constraints are coming from the data because we have some corresponding x and y, so that you can use those x and y to set up this relationship. And then the question is really asking to use simplex method to solve it. But apparently in this chapter, we didn't really study the simplex yet, which is supposed to be this week, week 6, you are studying simplex. So now I actually want to jump into simplex right away so that it's refreshed. Let's do this Monte Carlo simulation in this example first before we jump to the simplex. So if you look at this example, the problem we're trying to do is, the code here is trying to do is trying to use some sort of function to uh, to get some Monte Carlo method to minimize the absolute residual. So use 50,000 randomly generated new A and B using uniform distribution and try to calculate the difference. And then at the end, keep track of the best solution as steps keep changing, and then look at the solution graphically. So that's how we come up a solution here using Monte Carlo method. I think I suggest you that you can go through this and see if it makes sense to you. And then if we continue with this, next question would be how to use simplex method. Looks like I missed something here for the solution. I don't have the original code. Do I? Oh, yes, it's here. Okay, so for the simplex, you use LP solve, and then you try to set up the matrix, trying to get the relation, trying to set up the function so that you would have this function which is exactly as what we have in there as the constraint. For example, the first one would be r minus 3.6 plus 1.0 a plus b larger than or equal to 0. And then you can assume that you can move 3.6 on the right hand side so that your right hand side for the first constraint is 3.6. And then you have r plus 1.0 plus b being the first constraint. And then we have this here, and then r, so the first coefficient is 1, and second one is plus 1a, which is 1.0, and then plus x3, which is a b, is 3.6. So x1 is really r in this case, and then x2 is a, and x3 is b. And then correspondingly, we have the second constraints. And then how is it set up? So using that, put the matrix in there, and then give you your right hand side, and then your direction. Repeated direction, it happens that all of them is larger than or equal to constraint. That's why you can have this. And then the objective function, why it's 1, 0, 0, because as I said earlier, x1 is really the r, and then the objective function is minimize r, meaning that for the first variable, the coefficient is 1, and second and third variable, the coefficient is 0. So after this being set up, then next is really simple. You can use LP, minimize a function with some constraint and directions and right hand side, and then solve it. It's really, this is a solve. Where's the solve? Yes, I think this is a solve. After this solve, you can get a solution, and that solve results get that solution, and then you find that R is this, A is this, and B is this. In that case, these two are really the variables that we're trying to find. And then the first 0.92 is really the objective function in this case, which is the value of the R. Right. So and then we find the minimum is 0.92 in this example. And then this is actually from one of your fellow students' solution. I think it's very elegant, and it's great that this is being discussed there. And also, he continues to use ggplot2 to plot the data and take a look. And the solution is, Yeah, this is a comment that I have earlier. I said I was not using simplex yet, and I was going to share it this week, but apparently because one of your fellow students did it earlier, so I kind of borrowed his solution on this front, and then this is a solution for this problem using simplex method. Okay, any questions for this one? No? If not, let's continue with the next one. And then we have using least square to fit this model. I think now probably it's easier for you to do this either using computer or use the we discussed the normalization function and how to find A and B. Algebraically, of course, you can also use R to solve it and to get the A and B. And then in that case, because the textbook in this chapter discuss a method to get the A using some specific function, and then the A itself can be represented as this format, which is the sum of xi powered by n times yi divided by sum of xi powered by 2n. So you can compute this in R, and then you can get the corresponding A. And you can plot the curve, plot the corresponding responses so that you can see whether the model is doing a good job. For the next question, we see that we just want to fit the W is a weight of fish and L represent its length and see whether there's a relationship between W and KL cubed using the least squares criterion. And then you can do is similarly, you can find that K just based on as the previous example shows, you can get that K algebraically, and then you can solve it using R, you can find the corresponding K value. And then calculate the sum of squared error to see whether the error is randomly distributed. And here has some discussion. It's relatively speaking, apparently it is a good model. And then model 2 is using W equal to KLG squared. And then using the least square can we can find K is this. And then based on LG and W, we can find corresponding K. And then you plot the residual. You have corresponding values from two models. And here it says that the residual does show the model has some sort of bias in the data through the middle of the data set. Take a look. Why would we say that? But the problem here is only because we don't really have a lot of data points. So it's hard to make any sort of sound conclusion, even though we can see that here says in the middle, see apparently the residual are the positive. That's not randomly distributed, but here we see a little bit different. At least one of them is on the negative zone. So that's very general discussion. I think it's making some sense, but it's really not 100% accurate. Given that we only have this much data, with this many data points, there's nothing else we can do actually. So I still believe it's a reasonable explanation. And then that's this question. And then going to the next one, fit the model from problem 1 to 4 with the model, this model, compare the errors with the problem 4, compare the two models, which one is better. So model for the problem 1-4 is in this one, and then we have that data. You use population, velocity, and then try to fit it. We can do manipulation, take the log, and then we can transform it to a linear relationship. right? And then you can get your allowance C and A, which is a constant that we were trying to look for. Use linear model and then see that's the relationship. Apparently it's a nice linear relationship there. And then if you transform it back, V has this relationship with P, and then plot it. The model, relatively speaking, fits the data really well. If we try a different model, V is M this plus B, then you can try this directly. Take the log population, take the transformation, and then this is another model. And then that's the plot. Let's compare those two. Or compare the errors with the ones computed in problem 4 already. Compare those two. And then you can find that that's the error, and then any patterns there. You don't see any particular pattern, right? If you see all the red dots are above each one of the blue dots, you might consider, okay, the red, overall speaking, has a larger residual. And here we don't really see it. Of course, we can use some other metrics, such as sum of those individual error and see which one is smaller. That's another way to look at it. And then last session meetup, we also discussed we could use some even other metrics such as mean squared error, maximum deviance from the actual data, etc., absolute mean, absolute error, etc., so that we can compare the difference. And then which one is better? Let's take a look at them graphically. It's really hard to say which one is better. Only thing is, I would say argue here is the blue line has some sort of extrapolation risk because we don't have a population that's beyond 2.5 million. We don't have a lot of data observation there. So if we have a data of 5 million, there's potential risk that this blue line extrapolate much more than the red line. So in that case, we need to sort of thinking that red model, the line that represent the model represented by red line might be better in some regard, even though it really depends on in which direction that you are thinking about the problem. In some case, business insights or industry knowledge would help you to make the final decision on which model might be better in this case. And then the solution tried to look at 3 different criteria and come up with a conclusion. And again, this is by no means to be the only way to look at it. So, for example, if I'm going to take a look at this, I would pick the red model. I wouldn't take the blue line model, just purely because of the extrapolation risk. Let's continue and then look at this problem. And then x is the diameter of the pie again, and then y is the volume divided by 10. Make the scatter plot, discuss the appropriateness of using a 13th degree polynomial. First of all, you realize that it only have like 13 data points, and then you're trying to use 13th degree polynomial. Most probably, it's not going to fit well. It probably will be not going to fit well. So, and then we see this pattern. If you plot it, apparently it has some sort of problem here, and then it's just the degree of freedom is not enough to represent the data. So, and now that's basically the conclusion for this. And then if you test some other models, like the second and the third, probably fit reasonably well. I'll here discuss how to use linear model to take a look at this. First order linear model. And then next question, for this problem, we'll be looking at the fish data to see if there's a trend in the data, and then construct a divided difference table to see if smoothing with a lower order polynomial is appropriate. And then, so it is difficult to determine the outlier observation. The following code will compute the divided difference table. And then this is a code, and then based on this, we see the divided difference. And after, as per the divided difference values, a linear or polynomial of degree 3 is appropriate to the given data, just based on the observation of the divided difference table as discussed in the textbook. And then a model, here try to fit different models and try to compare the second order and third order, and then which one is better. It really doesn't matter whichever one you picked, in my opinion. But apparently, you got to have some sort of metric to evaluate which model is better. And then looking at number 5, the next question, number 5. And then the point was because you can make an argument either way, but here you have to start, you probably want to choose to start from 1971 because it didn't really have a lot of change before that. Because before this, right, apparently what we can also argue is we could try to fit the model all the way from here, but the problem with that would be before 1971, we really don't have a lot of observation. In other words, it could be some sort of outlier in this particular example. And then you use class shows a linear relationship against it. None of them seem to improve the linear relationship. However, it does have an issue that, again, it has this extrapolation risk because essentially saying that it will linearly increase as time goes by. But if you look at the data itself, it's probably true. It's just linearly increasing in the past as well. So that's the data and that's the model. Predicted value. And some discussion regarding that the stamp price will be 0.44 cents in 2010 and reach $1 by 2072. And in May, therefore, the prediction is reasonable. The stamp price was 0.44 in May 2009. Therefore, the prediction is reasonably accurate. It's a reality check in some regards. So that's pretty much everything for homework 3. So the most difficult question apparently is number 2. But we do have an example in textbook. As long as you set up the optimization problem correctly, even if you didn't solve it, you still get a full grade for this problem, I think. Okay, that's all for homework 2 and homework 3. If you have any questions on those two, just go ahead and ask. If not, if you have any other questions regarding this week's homework or last week, we can discuss as well. Even though last week I haven't got a chance to grade yet, but hopefully I will be able to do that before our next session. homework 5, because I haven't graded, that's why I would not be able to do that yet. Probably I would do that later this week or early next week, as I said, so that we can go over it. We are going to, I'm going to finish both homework 5 and homework 6 before our next meetup, so that we can go over those two in our next meetup. Actually, I didn't check the forum today, so let's go there and so that I'll see if I would be able to help. Yeah, I probably have some, so let me see if I can find it. The textbook doesn't give the textbook really, because it's not using R to solve any of the problems, so it can be used as a reference in terms of the solutions from the textbook. So let's go. So this is homework 6, right? Oh, it's not a homework solution.
Yeah, it is not a homework question. I just was trying to solve that question. It was interesting, so.
Yeah, if that's the case, why don't you just post your solution, and then we can try it and test it, and then see if you made any sort of error in the whole process.
Sure. I'm kind of surprised there because one of the boxes, I'm not sure if everyone looked into the problem, but one of the boxes was given as 0 there. Actually,
Yeah.
if you see the, so I was not sure if my solution is correct there. So.
Not necessarily. I think it's possible. It's possible that one of them is solution. It would be 0. But let's take a look at your solution and test it, and then we can provide
Sure.
more constructive suggestion.
Sure. Thank you.
Okay.
If you have time, could you discuss about the projects?
Yes. Hold on. Before we do that, Ruthie actually was asking about page 240 and number 2. Is that a homework solution, a homework problem?
Yeah, it was this past week's homework.
Homework 5. So I have this from one of the students earlier. So let's see if he is giving something that's making sense. Oh, but it's really just linear regression, right?
Yeah, I was able to do the one prior using the because I thought you said we had to do one of the questions by hand, I think.
Oh, no, I'm saying for simplex, for the optimization problem, first one. You need to do it. But not for this. For this, of course, you can do that as well, because you can calculate m and b as based on the normalization equation and find
Yeah,
those.
that's how I did the question 1, but I wasn't exactly sure if we'd be able to do it the same way for question 2.
Because it's a calculation is much more complicated, or what?
I think it was just cubed, I think, but
Okay. But in any case, yeah, for this one you can use calculator. You use it's not to say that you need to do this by hand. I was saying that for the simplex approach because if you use the optimization solver to solve the problem, you wouldn't get a sense on how simplex method itself is working. So I think it's important to at least do it one of the problem by hand for simplex for this week's homework.
I see.
Okay. So if we don't have any other questions, we can continue with a little bit discussion of the project. So let me pull out the discussion, I mean the syllabus so that we can. So as I mentioned here, you really have option of choosing either the project from the textbook, or you can select any problem that you actually kind of facing in your real work scenario. And then let's discuss option one first. For option one, you can find a section titled projects, and then you can form a team with at least one other classmate and complete any two projects. Or if you have three, if you have three people in your team, you could choose two projects as well instead of three. One thing that I really want to emphasize here is if you have a team member and then I hope that you guys are discussing the problem together, try to figure out solution together instead of okay, you responsible for one, I responsible for the second one. Of course that would work, and then I still hope that you have some sort of discussion with each other so that you're trying to solve the problem collectively. And then some of them in the textbook is rather straightforward. It's just a little bit more difficult than regular homework. So so it's really not too much depth in that sense. So in other words, and then for option two, it's some real world problem. You can think constructively think about the possible solution using all the possible modeling approach that we discussed in class. We kind of halfway through, but not yet. So as you can imagine, there will be more other possible solution methodologies for the problem. So hopefully that you can pick two out of all the solution methodologies that we are going to discuss in class, and then you can use those two and compare those two and find a better discuss that, not necessarily to see which one is better. At least you would be able to discuss what's the motivation you choose that methodology, and then what's the possibility that you can further improve the methodology. It could be better data collection, it could be better methodology, it could be that the initial assumption that you have made lead you to some sort of not really to the right spot. You can, even though it may not solve the problem, but if you apply the methodology, you can discuss that. Definitely, you can discuss that, and then try to put them into the report and into the presentation so that we can all hopefully provide some sort of constructive suggestions. And then, as I said here, basically in the report, it's essentially the same thing as what will be in your project as it progresses. So you can have some discussion of the analysis of the problem, the methodology you use, details of the methodology, and the findings from the project, and are they different from your initial expectation? If not, if so, is there a suitable explanation? If not, can you provide some possible solutions on further improvement, etc. So that's the idea. And then I said that you can, this is in general, there's a schedule here. You can form a team by end of week 8. And then you can have a project draft proposal the week after. I say it's draft only because I want to take a look and then we can discuss a little bit, and then hopefully I can give you some suggestion so that in week 10 you have a new proposal, even though it can be the same as well. Maybe I just say it looks fine, or maybe it's not enough, or it's too much for two of you, things in that nature. And then in week 10 we can finalize that proposal, and then in week 11 actually we can finalize that proposal so that you can get started in week 11, and then after that I think you probably have 4 to 6 weeks to finish the project, and you can present the results, and also you can submit your project report. Yes, you could just work on the problem, any of the project just by yourself, even though a teamwork is encouraged. Of course, if you know, due to your working schedule or due to the nature of the problem, and either no one is interested in, or because of some confidentiality of the data, you have to work on yourself, but just work by yourself is perfectly fine. Even you don't need any reason that you say, okay, I just want to work by myself, then that's fine as well. So do you have any questions that regarding the projects or confusions, so that I can try to clarify? No? Okay, so if you don't have any questions, we can just stop here today, and then because not every student is here, so I'll try to share the recordings as well, and then I'll go through homework 5 and 6 for next week, and then we can discuss more next week too. Okay, so thank you.